Good morning, good afternoon, or good evening. Whatever your case happens to be, I'm Teacher Kos, and in the previous lesson, we learned that energy stored in a capacitor is equivalent to what? May you tell us the expression? Can you write it down? You may pause a bit the video. Then the other expression. And the other one? Yes, we say that energy is equivalent to a half QV or is equivalent to a half CV squared or is equivalent to a half Q squared out of C. These are the three expressions that you got for the energy stored in a capacitor. Today we want to apply them in calculations, and we are presented with a question that a capacitor of capacitance 12 microcoulombs is fully charged from a 20 VDC. Calculate the energy stored by that capacitor, the energy supplied by the DC supply, okay, and then after account for the difference, if any, between the two energies, we can just start and we see what are we given. What are we given in this case? We are given the capacitance. So we are given capacitance as 12 microfarads. What else are we given? This one is charged from a 20 V DC supply. It's the only capacitor that we have. So it will take up that same voltage. So that capacitor is charged to a PD of 20 volts. So what do we have? We have capacitance and voltage. So when you look at this, we have capacitance and voltage. So we shall use this expression. Therefore, to answer our Roman 1, we shall say that the energy stored is equivalent to a half CV squared, which we substitute and we say this is a half. The capacitance is 12 exponent negative 6 times V squared, that is 20 squared. And when you press on your calculator, it should be giving you 2.4 exponent negative 3. 2.4 exponent negative 3. This is energy. What is the SI unit of energy? We have used standard unit. So what is the SI unit of energy? Remember, yes, it is in joules. So we have acquired the energy that is stored by that capacitor. Which is this? So we have a source, and then we have our capacitor here. Okay? This capacitor is of capacitance 12 microfarads, and this is 20 volts, as simple as this. So this can be the kind of the diagram that we have, right? And then another question, the energy supplied by this. You have studied from even the lower levels that the electrical energy, because that is electrical energy, that the electrical energy is V, I, and T times time. We are not given time, we are not given I, but we have known that I is the rate of flow of charge. Yes, meaning that our energy will be V Q out of T, then times T. So the T will cancel and will remain with VQ. But we are not given the charge. We don't have the charge. So what do? You know that expression that Q is equivalent to CV. So So therefore, this becomes V into the Q, which is CV, and therefore the V times V will be V squared, and the energy will be CV squared. That is the energy that is supplied by this, and by substituting this one will give us the capacitance, which is 12 exponent negative 6, then times V squared, that is 20 squared. You can even see from the expression, this is the half, this one has no half, so they won't be equal, and the answer will be 4.8 exponent negative 3, and it is still same energy, so the SI is a joule. Yes. So why is there a difference in Roman 1 and Roman 2? This is 4.8, this is 2.4. This is actually the half of this. What brings it? Remember the previous lesson. In case you have not had it, please check there on YouTube the previous lesson. You will be able to understand how we drive this expression. We derived where we found out something. It was almost the average energy required to drive an electron from one capacitor plate to the other. So we found out that for you to drive the very first electron, you would not need energy. But then for you to drive the very last electron, then you would need the energy equivalent to the potential difference, which was this. And therefore, we found that the energy required would be the average of the initial, which is 0, plus the final, which is the whole of it, then divided by 2. Okay? Now, look at this. What brings that? Yeah, of course, what happens is that some of the energy is used in what? In the wires, okay? Some energy is lost in form of heat in the connecting wires, and that one can account for what we may call the energy loss, okay? As we even add on other things, but much of it is the one that is lost as heat in the connecting wires. So that's the energy that is lost. That is not stored by the capacitor, but this time that is stored by in the wires, that is lost there in form of heat. That was our first question. We can have another one. We intend to have 3, so we can have another question, and it shall be as simple as we shall have a diagram here, and then we calculate. Meanwhile, don't forget to invite your colleagues to subscribe to our channel, BSc Science Education Consultants. So for the arrangement of the capacitors shown, we can have it here. This is our arrangement. We have the source, then it's connected to a certain capacitor of capacitance 5 microfarads, and then we have another capacitor here of 4 microfarads. We have another capacitor here, and we shall have another capacitor there. Okay, so this is 6, the other one is 2. This is 6 microfarads, and this one is 20 volts. So for this arrangement of the capacitor, then find the total capacitance of the arrangement is our first question. find the total capacitance of the arrangement, and secondly, the total charge that is stored when the capacitors are free charged. So we want the total capacitance and the total stored charge. So how do we get the total capacitance? You first realize which capacitors are in series, which capacitors are parallel to each other. So if you can begin from our diagram, look keenly, which ones are in series? The current will begin from here. It would flow. When it will reach here, it divides this to that and to that. Okay? It will divide this, this, and that. So you can see that the current through this is different from the current through this. Therefore, this and this are in a parallel arrangement. So you can say that 4 microfarads and 6 microfarads are in a parallel arrangement. Therefore, the resultant capacitance from the two is the addition. The 6 plus 4, which becomes 10 microfarads, is an addition. And when you look at the two, what they form, the resultant of these two will still be in parallel with that one. Okay? Therefore, this capacitance of 10 and the capacitance of 2 will also be in a parallel arrangement. Therefore, the resultant will be 10 plus 2, which is 12 microfarads. In short, somebody can say that this one, and that one are in a parallel arrangement. Therefore, you just add, just sum them, this plus that, as simple as that. Therefore, after getting that one, the resultant of these three is in series with this one. So you can maybe have this one, then that one, then the source. That could be the diagram. So this is 12 microfarads and this is 5 microfarads. So this one gives you that the two are in series. And how do we treat the capacitors in series arrangement? The capacitance will be the product out of sum. So that is 5 times 12 out of 5 plus 12 microfarads. And when you compute that one on your calculator, you are supposed to get 60 out of 17. I want to leave that one at that point. So that is 60 out of 17 microfarads. What does the question want? The question wants the total charge. And that's the one. Okay? Then we have a second question that is saying the total energy stored when the capacitors are free charged. You have the total capacitance. You have the PD that is actually charging that what would be that one capacitor. Therefore, it is as simple as the total energy. Total energy is a half CV squared, where this C is the total capacitance or the effective capacitance, which is this. And therefore, our total energy will be a half times 60 out of 17 exponent in 6, then times 20 squared. And when you can press that one on your calculator, you should get something close to 7.0 exponent negative 4. 7.04 exponent 7.06 exponent negative 4, and that is joules. So that is the total energy stored in the capacitor. And if you need now the total energy that is supplied by for example, by the source. You can also calculate it and you compare it with that, and you'll see some great difference, and you know the reason why. That is teacher course at Back Science Education Consultants. I would want us to have some proof here. We have some proof here, and it is a very nice one that brings more understanding, and then we can move on as we build for the future, as we do all this work to help ourselves. So our question is, a capacitor of capacitance C1, a capacitor of capacitance C1 is charged by a battery of an EMF V0. Is charged by a battery of an EMF V0. Full stop. The charging battery is then removed. The charging battery is then removed, and the capacitor is connected to an charged capacitor of capacitance C2. Is connected to an charged capacitor or capacitance C2. Show that the loss of energy after connection is given by. Show that the loss of energy after connection is given by E, that's the energy loss, is equaling to C1, C2 out of 2 into C1 plus C2, then V0 squared. Show that the loss in energy is given by that one. So what are we given? We are given a capacitor of capacitance C1. Okay? We have a capacitor of capacitance C1, which is charged to a PD of V0. And then we are told that this capacitor is connected to a capacitor of capacitance C2. So we shall have this our capacitor being connected to another capacitor with a capacitance C2. So this one is C1. What happens? What happens is that when you connect them, the charges redistribute themselves until a common PDV is across both. And here, we want to show that the loss in energy is that one. Meaning, we want to get the initial energy stored minus the final energy stored. Okay? So for us to get the final energy, we shall first get the final capacitance, right? As we studied in one of our previous lessons, we said that when these ones are connected, the charges distribute themselves so that this one works like it is a parallel arrangement. So that the effective capacitance will be C1 plus C2. And then we say that since there is conservation of energy, then the initial energy stored, stored charge rather, is equal to the final stored charge, because charge is conserved. You know that charge is CV. So the C1 V0 plus the C2 times 0, because the capacitor or capacitance C2 is not charged, is equal to the C1V plus the C2V, because they have common PD. So therefore, this is C1 plus C2 into V equivalent to C1 V naught. This one gives us the value of V when you divide by C1 plus C2, C1 plus C2. You have V as C1 V naught out of C1 plus C2. So that is the potential of that's the PD of the final arrangement. So therefore, what is that energy now? Okay, so the energy loss is the energy before connection minus the energy after connection. The energy before the connection is the energy that is stored by the capacitor or capacitance C1. Since this one, the C2 had no voltage, then since it was not connected to a PD source, then it has no energy. Okay? So therefore, this can be now a half C1 V naught squared. Then minus a half. What is the capacitance? The capacitance after is C1 plus C2. So this is C1 plus C2. Then the V of this is now this one, which is C1 V naught out of C1 plus C2. But the whole of this is squared. We want to perform calculations here, the mathematics, and we see whether we shall get that. Let's move. Let's go. So you realize we can first square. So this is C1 V naught out of 2, then minus C1 plus C2 into C1 squared V naught squared, then out of 2, then this one squared, C1 plus C2 into C1 plus C2. That's the C1 plus C2 squared. Okay? When I square this, I'm realizing that one of these will cancel with that. Okay? So that I remain with this one gives me C1 V naught out of 2 minus C1 V naught squared out of 2 into C1 plus this is C1 squared. Okay? Into that, we can handle the LCM. The LCM will be 2 into that. So we shall say that this is 2 into C1 plus C2, which is a good journey, because you can see we have it here, right? Yeah, that's a good journey. The moment you start getting some of the requirements when you are doing a proof, then you get energy. Please be energized. Even that one who was trying to doze, please, can you follow up? Please, come on board. Come on. Right? Okay? So, when I get this one and divide by this, the 2 will cancel, I remain with this, which will multiply to this. So that will be C1 V naught into C1 plus C2 minus. When I get this, I divide by this, I get 1. 1 times that. So it gives me C1 squared V naught squared. When I open this bracket, this will be C1 times C1, which will be C1 squared. Then this is V naught. So that is V naught. Then C1 times C2. Okay? Yes. Then plus C1, then C2. I think this was a V naught squared. right away from here, I think I forgot that. This one, V naught squared, even here. So even here. So this will be also V naught squared. Then subtract C1 squared, V naught squared. V naught squared. Then out of 2 into C1 plus C2. C1 squared, V naught squared, C1 squared, V naught squared will cancel. So we shall remain with this one has a V naught squared also. Yes, when we are this times this, it becomes C1 squared, V naught squared. This times this becomes C1, C2, V naught squared. C1, C2, V naught squared. Then C1 squared, V naught squared. This one cancels with that. And therefore, this one will give us C1, C2, V naught squared out of 2 into C1 plus C2. So, and by doing so, you can see that we are able to prove that the C1, C2, V naught squared, C1, C2, V naught squared out of 2 into C1 plus C2. So, by doing so, we are able to calculate the energy loss when the two capacitors are joined. So, these proofs are simple as just follow step by step, follow all the principles, all the procedures, and finally you'll get the answer that you want, and you'll have nothing like you can complain or you can meet anything that is complicated. That is if you only keep yourself at Back Science Education Consultants. You keep following all our lessons, you watch all the videos, and you take these videos not as watching, but you take it as a lesson. And please follow. When you have any question, raise us. We are available for you. Our contacts are available. Just check on our YouTube channel. All the information is there. I really like that. I like that. So, may God bless you. We are about to come to the end of this chapter. But after the chapter, we shall be beginning with other chapters. Please stay on, stay tuned. Don't forget to invite your friends to subscribe to our channel so that they can also enjoy. Thank you for learning with us.